This is section 10.5 where we'll talk about torque and the vector or cross product. Our objectives here are to define torque and solve some problems where angled forces create multiple torques on a system, and recognize the torque equation as a cross product and be able to apply cross products to solve some problems. Let's just start out by defining torque. Torque is the tendency of a force to rotate an object about some axis. The variable for it is a tau. It kind of just looks like a curly T. So torque is really this thing that actually causes changes in rotational motion. Just like a force would cause a change in translational motion, applying a force causes something to start accelerating or moving in a given direction, torque basically does that in terms of rotation. It requires a torque to change the rotational status of any object. Torques will start rotation, torques will stop rotation. And it is a vector. The units for it are the Newton meter. So we're going to see that it is a combination of both a force and a lever arm, or a distance that would be measured in meters. So what if you pulled on a wrench like you have here in the figure? What force actually contributes to the torque? What force would actually cause you to start rotating the wrench? Now obviously this force could be broken down into components. Some of this force is in this direction, and some of the force is in this direction. Now clearly, pulling on a wrench in this direction is not going to do anything to create any sort of rotation of that wrench. What I want you to recognize is that it is only the perpendicular component to the force that actually creates rotation. So pulling perpendicularly on something, perpendicular to the rotation axis, is going to now create some sort of a torque and begin to cause this object to rotate. So torque really is the product of the distance to that point of application of the force and the perpendicular component of that force. And that's what you see here in our equation for torque. Torque equals RF sine of the angle. Angle could be a theta, a phi, any one of those things to represent that. But ultimately what we're saying is that torque is going to be a combination of an amount of force that you apply and where you apply that force. How far away from the rotation axis is it? The more leverage you have, the further this distance is, and the more torque you're going to be able to apply. And of course, the more force you're able to apply, the stronger your torque is going to be as well. Now, torque is only defined when you have a reference axis that is specified. Where are you trying to rotate this thing around? And it would change values depending on how you define that axis of rotation. And again, remember, the parallel component of the force is not actually going to do anything in terms of creating rotation. Basically, its line of action passes right through the pivot point itself and therefore cannot add to the rotation in any way. Another way to interpret the torque equation is to write it as torque equaling F multiplied by an R sine of theta, or an R sine of phi. Really what we're saying here is that torque truly is a force multiplied by a lever arm, some distance away. So really this D here can be defined as an R sine theta. We would call that R sine theta, or that lever arm that we're talking about, maybe a moment arm or a lever arm of the force. This represents the distance from the rotation axis to the line of action of that force. And sometimes this approach is easier than breaking the force down into components. What we're really looking at here is that we could either take the force, like on the wrench that we just saw, and we looked at, the force that was being exerted maybe in, a direction like this. We could take this force and we could break the force down into components along the axes, or we could actually, instead of breaking the force down into components, we could leave the force as it is and instead look at a direct line from the force to the lever arm and define that now as the moment arm or the lever arm. That would be this R sine of phi or R sine of theta quantity that we're looking at here. I want you to notice that torque is maximized when you're looking at it, the force being exerted at a 90-degree angle. Essentially, we know that the sine of 90 is going to be 1, or the biggest value that you could possibly get out of this equation. Then it would truly be the force multiplied by that distance. As your force begins to become angled, this lever arm is essentially shortened. Or you could think of the components of the force now being less, so that only a part of that force is contributing to the rotation instead of all of that force. This is going to result in less torque and less of an ability to change the object's rotation. As we get the angle to be even tighter, again, less and less of that force is contributing to the rotation, or you can think of it as a shorter and shorter lever arm. But instead, maximum torque is going to occur at a 90-degree angle. Now, what happens if two or more forces are acting on an object? We can see in this case that we have person A pulling on this wrench and person B pulling. They're pulling with different forces at different distances away, so they have different F values and lever arm values. But just like we can sum up all the forces acting on an object or system, we can also sum up all of the torques. So notice that net torque can really just be a sum of all the torques acting on the system. We do have to, however, pay attention to direction, because if person A was pulling this way and person B was also pulling this way, their torques would simply sum together. We would add these two values up. But if person B was instead pulling in the other direction, then they would basically be working against each other. One person would try to be rotating it one way, while the other person's trying to rotate it the other way. In this case, we would actually subtract those torque values. So we do need to pay attention to direction. However, we have the ability to simply add torques up. In the case where they're working against each other, we would add these values where we have to include the direction of the positive torque being one that is causing counterclockwise rotation, and the negative torque being the one that is causing the clockwise rotation. So that's how we define direction with that. Don't confuse torque and force. Remember, torque depends on force and where that force is actually being applied. The units are actually the Newton meter rather than just the Newton. And torque is a vector. It does have direction, as we were just discussing. Anything trying to rotate clockwise is considered negative torque. Anything trying to rotate counterclockwise is going to be considered positive torque. And we need to add these torques together when we create that summation. We need to add them together considering those directions. Now, if we think about what happens if force increases or the lever arm increases, that would give us an idea as to which way this thing will rotate. For example, if we were to really increase person A's force, they might now have the larger torque and the thing will start rotating in this negative direction. But when we look at person B, if they applied a big enough force, considering the fact that they have the bigger lever arm, they might be applying enough force in order to have this thing be rotating in the positive direction in this way. We would add those torques together to see which way our overall net torque is going to be acting. So we can find the magnitude of the torque by using RF, sine of phi, or sine of theta. Direction, however, is a little bit different. In terms of forces, we were looking at translational motion. Everything just kind of was along an XY axis. However, here, when we look down from the Z-axis, these were your eyes looking down on this plane here, both force and lever arm would both be in the XY plane, and the thing would be rotating kind of all directions along this XY plane, always pointing in different directions. So as we look at this and we look down the Z-axis and see our force there and our lever arm there, really the only direction that is left to define the direction of the torque is in the Z direction. So looking in this case here, because this is causing a counterclockwise motion and therefore would be considered positive motion, we would define the torque to be up the positive Z-axis. Torque is now along the positive Z as the direction of that torque. If we were to switch the direction of the force and instead had the force pulling this way, therefore creating a rotation that would be in the opposite direction, or the clockwise and negative direction, now we would define the direction to be along the negative Z-axis. So it would be going down into the plane or along negative Z. So direction is going to be defined actually perpendicular to both the force and the lever arm values. These choices that we see here can actually be defined more clearly with a vector or a cross product, which is what we're going to define on the next slide. So the vector product or cross product is really just a mathematical operation, much like the dot product that we learned about earlier in the year. The cross product is taking two vectors, crossing them, where the symbol for the cross product is just a big X, and you take the magnitude of each vector, so magnitude of A, magnitude of B, and then multiply by the sine of the angle between them. So if this is vector A and vector B, we would simply find the magnitude of each of those vectors, multiply the magnitudes together, and then multiply by the sine of the angle between them. Now, torque can be defined in this way because really we said that torque was simply taking a lever arm and multiplying it by the force being applied times the sine of the angle between them. So literally, our torque equation could be more succinctly defined as an R cross F. Now, when you cross two vectors together, your answer is actually a vector itself. The magnitude is given by the two magnitudes multiplied together times the sine of the angle, but the direction is given by what we call the right-hand rule. The right-hand rule, there are several of them. In this case, we're using one where you point your four fingers in the direction of the first vector A, or R, and then you curl those fingers through the angle theta to vector B. Notice in the diagram that we have up here that this person started with all four fingers pointing up in the direction of R, the first vector. Then they curled those fingers over in the direction of F, the second vector. And now their thumb is left pointing along sort of this z-axis that you have here, and that is now defining the direction of your torque. Now, some properties of the vector product would be this. It is not commutative. A cross B is not equal to B cross A. In fact, it would be equal to the negative of B cross A. If you check this with your right-hand rule, you'd find that when you curl your fingers going from A to B versus B to A, your thumb's going to end up pointing in exactly opposite directions. Also, if A is parallel to B, saying that the angle is a 0-degree angle or a 180-degree angle, we know that the sine of 0 is 0. So any vector crossed with a vector parallel to it is simply going to be equal to a 0. So that means any vector crossed with itself will be equal to a 0. Now this really speaks to the example of the wrench. What we were saying is that if you have a lever arm vector being along the leverage of the wrench, and then a force vector also pulling along that same direction, this creates no torque. It creates no rotation because these two vectors are parallel to each other. If they're parallel to each other, as you can see by the cross product, you get a 0 torque and 0 change in your rotation. This would also mean that any components of vectors, like an I crossed with an I, a J component crossed with a J, or a K with a K, will also be equal to a 0. But what if the angle was a 90-degree angle? If the angle was a 90-degree angle instead, we know that the sine of 90 degrees is actually equal to a 1. So basically, this cross product is maximized at 90 degrees, and A cross B would be the whole A times B of those two magnitudes multiplied together. Again, this speaks to the example of the wrench, because if we applied the force at a 90-degree angle, we said that this would maximize our torque and create the greatest change in the rotation of that wrench when we apply that force at a 90-degree angle. If you try out your right-hand rules, you'd find that if you point your fingers in the direction of I and curl them towards J, your thumb will be left pointing in a K-hat direction. If you cross a J with a K, your thumb is left pointing in an I-hat direction. And if you cross an I with a K, your thumb is left pointing in a J-hat direction. We'll practice this a little bit more in class, let you practice your cross products and your right-hand rules to make sure that you all feel comfortable with that.